going to talk about lasers, fundamentals of lasers, and I'm also going to mention why lasers are very useful in medicine. So, about the ELI project, ELI is short for Extreme Light Infrastructure. This is a distributed research infrastructure. It's distributed because it's actually being built in 3 cities, in Prague, in Szeged, and in Mahura, close to Bucharest in Romania. The idea is to found research institutes where we are not researching lasers, we are using lasers to do research with them. So all these facilities, all these research infrastructures are laser-based research infrastructures, and they all contribute to the development of high-power lasers by setting new standards in the field, as well as, so this is a common aim of all 3 facilities, and they are also separated because they specialize in different fields within this high-power laser science field. And the specialty of our institute in Szeged is to generate very short pulses in the XUV and X-ray regime that are shorter than what you can achieve today with lasers. These are the so-called attosecond pulses, and this is why the acronym of our research institute is ELI-ALPS. It stands for attosecond light pulse source. So, what is an attosecond? How short is an attosecond? The shortness of time might be best visualized by how long distance light travels in a certain amount of time. And if you look at what light can do in 1 second, basically 7.5 times it could circle around the Earth in 1 second. And as you decrease the duration of time, going from second, microsecond, picosecond, these are just the SI prefixes before second, you see that in shorter and shorter times, it's smaller and smaller distances that you can travel if you are a light pulse. Basically, our field is the femtosecond and attosecond regime, so 10 to the minus 15 and 10 to the minus 18 seconds, and during this very, very short time, light can travel the width of a virus or the width of a molecule, also indicating that the processes that we will be able to, or we are able to study with these short pulses are of this spatial extent. The ELI project, it all started with the idea that Europe should have some research institutes where lasers are exploited. And actually the idea came in 2005. And then, as in Europe, we always set up a project, and there is a great idea. So there was a preliminary phase of the ELI project where scientists all gathered together from Europe, and they looked at what is possible. So they made a feasibility case for ELI. And then during this period, till 2010, they decided that this would be a very, very good opportunity for European and worldwide scientists to build a research institute. And then the decision was made that 3 research institutes are to be built, and one, Hungary with Szeged as a site, proposed to host one of these research institutes. And just outside Szeged, there was an old Soviet military base that was vacated by the Soviet army, and it seemed to be a very good idea to, this territory was owned by the university, and the university donated this space to the project. And this is where the construction started. So in 2014, as Professor Varjú said, 3 years ago, construction has been started, and first there was a very scenic picture that you could see with all the cranes. And then it took the construction company 3 years to build the research infrastructure, and this is something that you will visit, and you can hopefully appreciate foundation was made underneath the laser holes. The area, as being close to the river, has a lot of sand in it, which is very good for vibration isolation, but you would also need something to hold the weight of the building. So actually the solution that the engineers have found is that they drilled down 40 meters to the ground until they have found a layer which was rigid enough to hold the weight of the building, and then they started building from the pillars the whole building. To decrease the weight, they designed a very special honeycomb structure. So engineering-wise, the building was very complicated, but it seems that the effort was worth it. And now we are occupying the building for now a month. The construction was finished in 2016. End of 2016. Already at 2015, the outside shell of the building was done, but the full construction was finished last December, and this May we had an inauguration event with cutting of the ribbon by the Prime Minister, the former head of the Ministry of the Academy of Sciences, the mayor of the city, and our managing director. And I just show a few photos of the building, but you will be able to see it for yourself. We have a 200 people lecture hall, which is resembles, the shape of it resembles the brain, or at least that was the intention of the architect. And we had Professor Krauss, a well-known scientist in anti-second physics, come and give us an opening lecture for the inauguration. So this is what the building looks like from a bird's view. This is the technological building, Building A. This is going to house all the lasers and the experimental areas. In Building B, we have some auxiliary laboratories that don't require this very severe vibration stability issue that Building A has. In Building C, we have the offices, lecture halls, library. This will be shown to you when you visit the facility. Just some interesting facts about the construction itself. So there has been a huge amount of soil that had to be removed from the foundations of Building A, as well as we have a rain reservoir outside, because the constructors had to take care of the rain water collection of the area, because this was a new area. We are the first occupants of the area, so this is also something that had to be taken care of. As I said, the building is standing on piles. In total, we have more than 800 piles, and these piles are holding the structure. The total amount of concrete that has been put into construction would fill 18 Olympic swimming pools, and the total length of the piles is much higher than the rest. So this, I just use these numbers to illustrate the construction itself was already a very big deal. And now we have the building finished. We have the laboratories. The laboratories we specified to very strong conditions. To operate these high-power lasers, we need the air of the laboratory to be very clean, because if there is any dust that goes onto the laser mirrors, then it will damage first the quality of the beam, and then it will be the diffraction which will be burned into other mirrors. So we have ISO 7 and ISO 8 cleanliness level of the laboratories. It means that in every cubic meter we have less than 10 to the 7 or less than 10 to the 8 particles, number of particles. Also, whoever worked with lasers know that the lasers are very picky about the conditions, about about temperature and humidity. If you set up your laser at 21 degrees and the temperature goes off by 1 degree, you have to realign your lasers. So this is why we asked the constructors and the engineers to make very stable conditions, very stable environment for our lasers. And as I have already mentioned, we have to be very strongly isolated from external vibrations. And also we put a lot of effort in not creating vibrations in the laboratories themselves. You will see that all moving components are put on so-called engineering bridges, which is vibrationally decoupled from the laboratories. The reason is that with these high-power lasers, we are planning, we are designing optical arrangements that are 10, 20, 40 meter long. And if you shoot 40 meter away, you still want to hit that mirror in the exact position every time you shoot. So you have to have a very good stability of your whole system. The scheme of ELI is that we have so-called primary sources, and these are the lasers. And all our experiments rely on using these lasers. With the lasers can be used for experiments directly if someone wishes to use these very high power pulses. Additionally, the laser pulses can be used to generate secondary radiation, or rather I say secondary sources, because the secondary sources span from other light pulses, very wide range. With the near-infrared laser pulses, we create X-rays and we create terahertz pulses as well. I heard that someone is interested in applications of terahertz radiation. We are also producing terahertz radiation. And then for the experiments, we have a few ideas in what research directions we can experiment into. But since our institute is going to be a user infrastructure, a user facility, we also prepare ourselves for the arrival of users who might just come in with an idea that they would like to test this molecule, and then we have an experimental arrangement where they can just input this molecule and see what dynamics we can deduce from the experimental data. Or we actually have standard endings of our radiation sources, so if someone comes with a complete experiment, they can just dock it to our beam lines. The main lasers that we have, I just listed them here, and these slides will be available for you later on, so you can look it up. These are all pulsed laser. I'm coming in a minute to explain you what pulsed laser means, and they are all state-of-the-art. They are really cutting-edge lasers in their own sense, and I'm going to explain you how these very different characteristics laser could all be cutting-edge and state-of-the-art. And as I said at the introduction, our main aim at this institute is to pursue experiments in attosecond science, attosecond field, and this we hope to achieve by these different lasers and the generation of attosecond pulses with these lasers. Basically, the properties of the attosecond pulses that we can produce derive from the properties of the lasers that we have to use the production of attosecond pulses. And the properties of the laser pulses is always a trade-off between the different parameters. If I just go one step back, you can see that there is a laser running at 100 kilohertz which produces 1 millijoule in every pulse. And there is a laser which is producing at 1 kilohertz 45 millijoules pulse energy. So you have to, when you design your experiment, you need to know what you are aiming at, and you can either get very high repetition rate or you can get very high pulse energies, but you cannot increase both parameters at the same time. So our aim is to try to get better characteristics of the attosecond pulses, at least in one dimension. The three dimensions are the photon energy that we can reach, so we transfer from an infrared laser pulse towards XUV and X-ray ultraviolet or the X-ray regime. So we either increase the photon energy or we increase the intensity of the radiation that we are producing, or we increase the repetition rate of the pulses, how frequently they come. Presently what is available in different research institutes, university laboratories throughout the world are sources which fall in this part of this parameter space. And then what we hope to achieve is either get a source which is higher in repetition rate. We are trying to increase the repetition rate by 100 times by using a laser that has a repetition rate which is higher than ordinary university laser systems. And this way we can do studies that rely on very high repetition of the process, where we only get a hit, we only get some data recorded which is very low, coming out hardly out of the noise level in a single interaction. So we have to accumulate for a large number of shots to have a good statistics of what is happening. So this 100 kilohertz system is going to assist us in this sense. With a lower repetition rate laser having higher pulse energy, we can aim for a more intense attosecond beam, which means that we are having a larger number of photons in this beam, and then we can use it to induce certain laser matter interaction that requires a high flux, because it's probably a nonlinear interaction in this regime. Or the third possibility is that we don't put that much emphasis on repetition rate or intensity, but we are trying to reach as high photon energy. High photon energy means very short wavelengths. So we could reach very hard X-rays with these types of sources, and then we can do studies that are stronger bound or lower level, for example, core states, or we want to look at samples with radiation in the virtual window. Just introducing you the last slide about ELI. ELI is a bit more than the lasers. It also has the value of researchers from the people it employs. This is the scientific directorate that I'm showing here, and I'm also indicating on this plot how the number of people employed in the scientific directorate is increasing with time. And if you think that you would be up for the adventure of using these very high power lasers, we always welcome further applications at the institute. Okay, so the next part of my talk, I'm going to introduce to you some basic ideas about lasers. So what is laser? Laser, the word is an acronym. It stands for light amplification by stimulated emission of radiation. And basically what we should all know about lasers is that this is a light source, light with very special properties coming out of the laser scale. The laser idea, the atomic physics of the laser idea was worked out by Einstein in 1916. So the idea of building a laser comes from that age. But we had to wait until 1960 for the first laser to start operating. So this is how from theory practice comes at a slow pace sometimes. So this is what lasers, if you look at lasers from different angles, what we might see. So I said that it was 1960 that the first laser in the research institute started operating, and already in 1964 the idea come back next year, this is what you will see. Just boxes. You cover everything and you just see boxes. And what's inside the boxes is mirrors, crystals, all kinds of optical elements that is positioned at the perfect point. And then this miracle of laser operation happens. Lasers are all around us. It would be very difficult to find an area of our life where lasers are not used. It's used now in medicine, of course, in everyday life, like a barcode scanner. My little pointer has a laser in it, but we also use it to store data on CDs, DVDs. It's used in industry to cut very precisely. It's used in showbiz, and well, I think I've said most of the areas that came to my mind when I prepared this slide. So, what is a laser, other than just the acronym, and why is it special? This is what I'm going to discuss in the following minutes. And then I'm going to tell you why these special properties are, how they come about, what do you need, how you build a laser, basically. I'm going to introduce to you the main components of lasers, and these main components will ensure the special properties of the laser beam. And then, in the end, I will tell you what I think, why I think these properties really qualify lasers an ideal tool for medical applications. So, as I said, laser is just a light with special properties. So, everything we know about light is true for lasers. Just a few examples. You focus light, laser light, the same way as you focus ordinary light. Laser refracts at surfaces. The relationship between frequency, wavelength, and the speed of light satisfies this relation as every other light. And laser light can have different wavelengths, different frequencies, the same way as ordinary light. But we have some additional properties. The first one I want to mention is called monochromaticity, and it means that the beam, the light which is emitted by this source, by the laser matching, has a single color. So it's either red or blue or even invisible. It can be UV or IR laser. It has a very narrow bandwidth, and as a consequence of this very narrow bandwidth, it has a very nice temporal structure. We call it temporal coherence, which means that the light which is emitted from a laser source now and in a few seconds or a few minutes still able to interfere because the phase is very, very well ordered. I have here some example. So from a laser, the light that comes out would be a sinusoidal form, and if you would break it at certain points, then this would be incoherent, temporally not coherent, and also it would mean that the bandwidth is increasing each time you break this nice sinusoidal wave. Another special property of laser light is that the beam is very, very parallel. We say it's well collimated, or it has a small divergence. I have here some light source that can either emit a laser beam or it can emit white light. And you can actually not see white light, although I'm pushing the button, because this is not that well collimated. It is expanding. And you can only do it with a laser beam, that you keep it very much collimated. So you can even shoot a laser beam up to the moon, and you can still keep its spatial extent to a limited value. This small divergence of the laser beam also has a consequence that you can focus it very tightly. In optics, the first time you learn optics, you learn that in the focal spot of the lens, it's almost zero extension of the light. So you can collect the sunlight with a lens, and you can additional effect is that there are certain types of lasers that are tunable. So you build a laser. Dye laser is a very good example of that. That has been mentioned that dye laser science was done in our university. So you build a laser that is very monochromatic, has a very well-defined single color, but you can tune the wavelengths. This single color can be at a different value. And lasers can be made of very short pulse durations. We measure the pulse duration in nanopico or femtoseconds of laser bursts. And you see the range 10 to the minus 9, 10 to the minus 15 seconds. This is again something that you need a laser beam to be able to compress temporally the pulse very strongly. And actually all these properties result in the property that you can focus the beam to very high power. So you can have a very intense field in the focus of your laser. A bit of quantum physics of what the laser principle means is we know that matter and light can only communicate in bunches of energy. Photons, we say that photons have a certain amount of energy. This is the energy quanta of light, that it can exchange energy with matter. It depends on the wavelength or frequency of light, and these bunches can be transferred to matter to bring the matter from one energy state to another energy state. So just very simply, I indicate matter by these two energy levels, the ground state and the excited state, and I say that this matter can interact with light if light has the proper frequency, if the energy in this photon can make the transition between the ground and the excited state. So there are three basic processes, and this is what Einstein wrote down in his paper in 1916, that an incoming photon can bring the ground state atom to an excited state. In this case, the photon is absorbed, it's gone. So after the interaction, there is no photon, but the originally ground state atom is now in its excited state. This is called absorption. The other process, the inverse of it, is called spontaneous emission. Here we have no incoming photon, the atom in the excited state, and after the process has gone, the atom is in its ground state and the excess energy is given out in form of photon. And these two were known before Einstein, but he suggested that there could be a third process that he called induced or stimulated emission, where you have an incoming photon and it meets with an atom in its excited state. And somehow this photon makes the atom to go from the excited states to the ground state, so it stimulates this transition. And the main point is about the stimulation, because then the incoming photon and the other photon that we get from the energy difference of the two levels will be linked together, which means that these photons will have the same phase, so they are going to be coherent. And when you go through with this light, you meet another atom, then the number of photons that are interlinked is increasing with every interaction with an excited state atom. And this is what Einstein figured out, that if we could exploit this process, this would make a very special light source. And this is what we call the laser. The production of this laser light relies on how effectively we can induce this stimulated emission. And if you think about, there are two processes that the photon and the atom can go through. If the atom was originally in the ground state, then it's going to be absorbed, the photon. If the atom originally was in the excited state, then we get the stimulated emission that we want. And just a very crude understanding of what's happening, if we have a higher number of atoms in the excited state than in the ground state, we have a higher chance of the photon photon hitting an excited state atom, which means we will have higher number of events, higher number of stimulated emissions than absorption, and this is what we need. So this is what we need to do to make a laser, to put more atoms in an excited state than in the ground state. This is not what usually happens in nature. In nature, we have the thermodynamic equilibrium, and the lowest energy level is building first, and the higher levels have a lower population. So this is a non-natural way of the material, but in certain materials we can reach this population inversion, so we can put higher number of atoms into an excited state than in the ground state. And this is a very fundamental prerequisite before we can operate a laser. There are certain materials, and these are the laser materials that can be used, where through some transitions between the different energy levels, we can reach this population inversion. To run the laser, we have to put in energy all the time. We have to keep up this population inversion, but I'm coming back to it, how it is realized in lasers. So the major steps in producing laser light is to find a lasing medium, an active medium, that we can bring up to an excited state, and we can exploit the simulated emission process. This active medium we put between reflectors, between mirrors, because we want light to go back and through this active medium to gain at each pass more and more photons. So what happens is that we have this arrangement of the active medium and the resonator with the two mirrors, and then through some energy transfer to this medium, we bring the atoms to excited state. So the ground state atoms are indicated in green and the excited states in purple. So we have now, through this pumping scheme, some excited state atoms. And then these excited state atoms will start radiating light just by spontaneous emission. They will emit light, and then this light can start its propagation in this medium. And when this spontaneously emitted photon meets an excited state atom, then it can produce stimulated emission radiation. And then going back and forth, each time it passes through the medium, the number of photons is getting increased. But this is not the useful part of lasers, because this radiation, this very intense light, is now kept in between these two mirrors. We have to get some light out so that we can apply lasers, we can use lasers for something. So actually, one of the end mirrors in this resonator has a leakage, and whatever is leaking through is a loss for the laser itself, but this is the beam that we can use. So how do we build a laser? It's pretty much like Lego. You just have these optical components, and then you put them where they have to be put, and this is what laser physicists do. They figure out where you would put certain elements so that the light can travel as many times as needed through the active medium, not too many times, because if it's too many times, then you will start having losses. You also have to pump up your system. The population inversion need to be kept up. And there are quite a number of components that is needed for the operation of the laser. But these are the main functional parts that I have already introduced. The lasing medium, the active medium, the pumping scheme to bring the active medium up to population inversion, and the end mirrors of the optical resonator. much light here, then it means we cannot keep up the laser mechanism in the resonator because it's too glossy. If we are not letting enough out, then our laser beam will not be strong enough. So this is a trade-off on how much reflecting we want on this partial reflector. And additionally, we have a few other components. We need voltage supplies, control circuits, cooling system, and so on. But these are the functional parts of the laser. The first laser that was operated in 1960, that was the Ruby laser. It was a very simple architecture, very simple design. There was an active medium, this rod. The ends of this ruby rod was actually polished very nicely and then coated for reflectance. So basically the rod itself was the laser medium and the cavity at the same time. And outside you see here this pinkish rod, that's the ruby rod, and externally there was a glass tube wound around, and through a flash was generated in this tube, which means that photons were emitted in this flash, and then these could be absorbed by this ruby rod, and this is how the population inversion was reached. This is how the system was pumped, and then at the output, at the end of this rod, laser light was emitted. Lasers come in very different sizes and very different shapes. They can be as small as this one, or they can be as large as occupying a laser ball, which is as big as 3 football fields. Also, it can have a different type of active medium, and I'm going to talk through this now. So, the active medium of the laser, what you use for this stimulated emission. The color changed a bit. So the active medium. The active medium that we choose will define what is the wavelength that the laser will operate at, because depending on what are the energy levels in this material, certain transitions can be exploited for laser functioning. And there are, if you just search in Google and you put laser wavelength, you will get tables where it's indicated that whatever wavelength radiation you want to use, what type of material you should be using for your laser. But actually nowadays you are not building your own lasers, but you are buying them. But this is just indicating how you could get virtually any wavelength of radiation that you want. And why would you want to say which wavelength you want your laser to be? Because this radiation will, depending on the wavelength, will communicate with different type of material. It can address different materials. I have here the absorption spectra of just 3 different materials that might be interested in medicine. Oxyhemoglobin, water, and melanin. And you see it has some spikes in its spectrum, meaning that certain wavelengths are absorbed much better than others. So depending on what you want to address, what material you want to address with your laser,